Okay, welcome back. Sorry for the little delay I had here, a little technical problem. Anyway, welcome back. Hope everyone had a good week. Just a couple of things. One, remember that the next exam, okay, opens up due tomorrow. So don't forget, very similar to the previous exam, no exam number one, and about 23, 24 questions. There's probably about 4 or 5 kind of fill in, input your answers type of questions, and the rest multiple choice. Okay. Well, any questions on your part? Because if not, I will continue on to chapter 7, which is a little bit long chapter. Might spend definitely all the time we have today, and maybe a little bit next time. Okay. So if not, let me continue then. All right. Well, if you do have any questions, send me an email. I'll see if I can answer them after the fact. I do have a student coming in after our session here for like visit time at 4 o'clock. So you're free to hang around if you have maybe you came up with questions about the exam or whatever, or any of the questions concerning the chapters, so 4 o'clock, I'll be here for that. Hang around for a little bit. Okay. Well, let me continue then. Chapter 7.
I just had a quick question. Did you post last week's class on your YouTube thingy? Because I couldn't find it.
It should be there. Yeah.
I only found the one from before last week. So it was the September 16th.
Really? Okay.
I know you go over like other stuff in your in your GCU classes, but
well, let me find out what happened there. Okay.
Okay, no worries. I just want to let you know. I was just looking for it right before class and I couldn't find it.
Okay, so that would have been the 23rd.
Yes, indeed.
23rd recording. I will find out, see what happened to it.
Okay.
All right. Yeah, thank you for that heads up there.
Oh yeah, I was just trying to watch it before the exam tomorrow, and I was like, where did it go?
Okay, well, I will definitely after class today, or maybe during the break, I'll go up there and take a look and find out. Okay. All right. Yeah, I'll get that figured out. All right. Well, this particular chapter, we're getting into some chemistry here. Okay, we're going to start talking about chemical bonding. And here's the thing about chemical bonding. With respect to the chemistry we're dealing with, there's going to be only 2 types of chemical bonding. Okay, only 2 types. You would think there'd be like, a dozen more, but there's only 2 types. And what it amounts to is as follows. When you have a combination of a metal and a non-metal, okay, when you have that combination, you have what is called an ionic bond. Okay. Now, in that particular case, it's why it's so important that we understand from the elements what element is a metal and what element is a non-metal. Okay. We're not going to do a lot with metalloids, maybe a couple examples here and there, but more on that down the road. Very little metalloids. So when you have a combination of a metal and a non-metal, you have to know, okay, this is a metal, this is a non-metal. Then automatically what I have is an ionic bond. Okay. I have an ionic bond. Now, a good example of this is something you put on your French fries, good old-fashioned sodium chloride. Now, I know you're used to the term salt. Okay. Now, with respect to chemistry, all around chemistry, a salt is not just sodium chloride. A salt is a combination of a metal and a non-metal. Potassium chloride, sodium chloride, magnesium chloride. I'm using that as an example. Those are salts. Okay. Furthermore, they are ionic bonds. And I have a trouble with the term ionic bond, but that's what the industry uses, so I'll stick with it. Because in reality, when we're dealing with an ionic bond, there's no true bond. It is what we call a electrostatic attraction. And the best example I can think of an electrostatic attraction are two magnets coming together. Okay, there's no coming together with sharing. We got two magnets, they're just attracted to each other because of their particular polarity, north, south pole, etc. Okay, and ionic bonds are the same thing, because what's happening is we have a full-fledged ions that come together. We have a full-fledged positive ion, okay, and it could be +1, +2, +3, depends on the metal, combining with a full-fledged negative charge, which could be a -1, -2, -3 charge, okay? They come together because opposites attract, positive and negatives attract. And so when they come together, they're just together and attract in that sense. There's no true bond. Now, that's an ionic bond. Now, the key aspect about ionic compounds is this. If you take a molecule that is an ionic compound, normally they have ionic bonds, so it's an ionic compound, okay? When you put them into water, they will dissociate back into the ions in that solution. And some will dissociate completely 100%, and we're going to learn about that with the solubility rules. But some of them maybe not as much, but all of them will dissociate and break up into the ionic ions, okay? Unlike what we call covalent bonds. And that is a combination, I'm just going to shorthand it, say non-metal combined with a non-metal, NM, okay? Not New Mexico, but non-metal. Two non-metals coming together. We call that a covalent bond. And a good example of that, which is ordinary water, okay? Good old-fashioned H2O. We have two nonmetals, hydrogen's a nonmetal, oxygen's a nonmetal. They come together to form a bond, okay? A true bond where they are actually sharing electrons. And so we're going to learn about writing these structures. And the way I'm drawing water right now is I got oxygen, which is the central atom. We're always going to have a central atom. And you'll be told who the central atom is. You always know who that is, okay? And then everything else that is bonded around the central atom. And I designate that by this particular line. That line represents a bond between the oxygen in the center and the hydrogen on the right. And the same is true for the left side. This is an covalent bond, okay, on the left side with the oxygen and the hydrogen. On that bond, that line represents two electrons. Those two electrons are being shared with the oxygen and the hydrogen, okay? And there is actually, whereas ionic bonds just basically come together like my two fists here, and just attract with each other because of their respective charge. Covalent bonds actually interlace themselves in that bond, where that bond, here my fingers are interlaced, and they're sharing those two electrons. Now we're going to learn that sharing can be an equal sharing or an unequal sharing. I'm going to learn a lot more about that. And that is dependent on, remember we talked about electronegativity, okay? It's all coming around, hopefully putting it all together. So these are the type of bonds that we're going to be talking about, covalent bonds. Now, as with the ionic bonds, and I stated, I put them in water, they dissociate. Covalent bonds, when I put them in pure water, will not dissociate. They maintain their structure, okay? They maintain the structure. So if I take carbon dioxide, which is covalent, carbon dioxide, and I put it in water, it does not break up into carbon and oxygen, okay? Now, how do I know that? Well, let me tell you. I can take pure 100% water and check for conductivity if it conducts electricity. 100% water, pure, nothing else in there, will not conduct electricity. What conducts electricity is the fact that you have ions in solution. So if I take an ionic compound and I put it in a 100% water solution, it would dissociate to form ions, and it would cause, it's like the light switch on your light. It closes the switch or opens the switch so electricity goes through. Okay, and that's ionic compounds make solutions that are conductors of electricity, whereas covalent compounds, when you put them in solution, I take carbon dioxide and I bubble it through water, it still remains non-conductive because carbon dioxide doesn't break up. Something else happens, but it doesn't break up to form an ionic compound, and nor does it pass conduct electricity. Okay, there's only one exception that we're going to talk about of a covalent compound that will dissociate, and that's only acids. Okay, acids are compounds, are covalent compounds that will dissociate. A good example with what's in your stomach right now, hydrochloric acid, HCl. HCl will dissociate in water to form ions and conduct electricity, even though it's covalent. But that's the nature of the beast for acids. So right now, at this point, covalent compounds don't dissociate until we get to that chapter dealing with acids. And we'll have a lot more to talk about that when we get to that. Okay, so make sure that you do use the shapes table. It's on the website. I mean, on the website, in one of the modules, one of the two tables that you needed to print out. Obviously, the periodic table, which we will use quite a bit here. By the way, the solubility rules here on the right side, and then we're going to be using not only the periodic table, but we're going to be using this table within the table here on the left side, bottom left side, called the common polyatomic ions. Okay, but also we're going to be utilizing the shapes table. Okay, on the shapes table, there's some cancel this. There are four columns. Okay, we have what is called the generic formula. We're going to talk about this generic formula, ABE, which represents multiple things. Okay, we're going to determine from our compound what general formula we utilize, and from that information, if we determine it's an AB4, then this is the geometry for a general formula, a compound with the general formula of AB4. Okay, and this is kind of gives you a three-dimensional model of what we're looking at. Okay, and then it has a specific name called tetrahedral, and then there's a specific bond angle associated with that shape. Okay, and that bond angle is right here, represented by this line. That represents the bond angle between what is bonded to the central atom. Notice that in the middle, there's always going to be a central atom, and then everything else is bonded to the central atom. So we're going to be using the shape table quite a bit so we can determine the geometry, the molecular geometry of the compound. So, print that out so you become familiar with it. We'll be using it. Okay. Now, atoms, the driving force for these bonds that we're going to talk about is the octet, trying to get a configuration where there is 8 electrons around its valence shell. Unless you're hydrogen and helium, remember they have their own little duet, okay, 2 electrons around. Okay, so that means this, that let's take an example here of an actual molecule. We're going to learn more about this here, but I got a bond between carbon and chloride. Okay, now in this configuration, this is hydrochloric acid when it's in solution, or hydrogen chloride if it's a gas. Is, if you notice here, this line represents a pair of electrons, and I drew a line, but I can also draw it with 2 dots, and that's okay. Either one will work. Problem I have with the dots is I can lose a dot along the way, so it's just easier to draw a line. And so these two are the same thing. representing the same thing. So there is a pair of electrons that are being shared between the hydrogen and the chloride. Okay, so they count, that bond there counts to both the hydrogen and the chloride. So there are 2 electrons around being shared for hydrogen. So its duet rule is fulfilled. And if we look at the chloride, we have 3 pair, okay, 3 pair of electrons, or 6 electrons around the chloride that are not bonded to anything. And then the 2 pair that are shared with the hydrogen. So guess what? We have a total of 8 electrons around the chloride. And that is a driving force to obtain that either duet for hydrogen, which always will be the case, okay, and trying to get 8 electrons around the outermost shell on the other elements. And the driving force is for ionic compounds. You know, metals will want to lose electrons, now they become isoelectronic with the noble gas behind it. And for nonmetals, they want to gain electrons, become isoelectronic with the noble gas in front of it on the periodic table. Okay. All right. So that's our goal, the octet. So we know about this. We talked at length. Put it in long-term memory. Metals lose electrons. Okay. If you don't know what a metal is, and go to their periodic table, look for that stair step. To the stair step, on the stair step are the metalloids. To the left of the stair step are the metals. So let me do this. Yeah, shrink it here a little bit. All right. Here's the stair step right there. Okay. That is the metalloids. To the left are the metals, okay, and to the right are the nonmetals. With the exception of hydrogen, it happens to be in the side with the metals, but it's not a metal. Remember that, it is a nonmetal. It's on the first column because it has 1 valence electron, just like all the other guys do here in that first column. Okay, so we need to know who is a metal. All right, so we talked about this, cations, okay? Nonmetals gain electrons, and they want to become, and they become anions. Now, back to the periodic table. The question is, well, how many electrons do they gain, right? But that's answered by, and for FYI, for the nonmetals, by and large, we're going to be working with most of the ones I've marked here. Okay. Carbon, group 4, it depends on the conditions, but all the other ones are going to, with nitrogen, oxygen, fluoride, etc. Okay. The number of electrons they gain, it depends on what group they're in. And being that group tells you group 5, that's 5 valence electrons. They're trying to maintain the octet. Guess what? They need 3. Therefore, these guys all end up with a -3 charge when the atoms become ions. Okay. Next group over, they had 6 valence electrons. They need 2 to get the octet. So they end up with a -2 charge. And then finally, the group 7, they're only 1 electron away to get that octet fulfilled. So they pick up 1 electron and end up with a -1 charge. Okay. On the other end of the spectrum, the metals for group 1 and group 2, group 1 always a +1 all the time. Okay. Group 2 always a +2, 100% of the time. And then the other ones that I got blocked off here, I got aluminum at +3, zinc at +2, silver at +1, cadmium at +2. Everybody else varies. We don't know. We can't predict. Those 16 you can predict, and those negatives that I just anions, you can predict 100% of the time. Okay. All right. All right, so metal, non-metal combination, as I discussed earlier, is what we call an ionic bond. It is the attraction between a full positive charge and a full negative charge. Okay. And so if we look at these two, you're never going to find, I shouldn't say never, because science is not never 100%. There's always exceptions to the rule. But it's highly unlikely that you will find two positives coming together, at least at Chem 30 level, Chem 130 level. So the ideal partner is going to be a positive and a negative coming together to form a ionic bond. Okay. And so examples are a metal-nonmetal combination such as KCl, which is potassium chloride. Notice the name change too. The chlorine, when it becomes ionic, became chloride. So the name now becomes, for KCl, is potassium chloride. And then we have calcium bromide. Now, some people might think, look at this formula and say, hey, wait a minute. I got calcium Br2. They see the 2 here and they might think diatomic, okay? You might think diatomic, but that's incorrect. Why? Because what's in front of the BRs is a metal, okay? And normally when we write the formulas for ionic compounds, what we write, what is written first by convention is the metal. Notice we got potassium chloride, calcium chloride, magnesium bromide. The metal is written first, and then the non-metal follows. So if this were, if this were just written Br by itself, yes, then that would be diatomic bromine. No questions there. But the fact that there's a metal in front, followed by the Br, should say that this is not diatomic. It is no longer bromine, it is bromide. Okay, this is bromide because it's attached to the metal. And when there are more than one nonmetals, as a general rule, the calcium, the metal, is the central atom. I mentioned earlier, we're going to have a central atom and then everything gets bonded around it. So when you have more than one nonmetal, the metal is the central atom and the nonmetals are bonded around it, okay, as a general guide. Okay. With respect to nonmetal combination, two nonmetals coming together to form a compound, because that is the definition of a compound. Two different elements coming together, okay? And that is what forms a compound. So in this case, we have examples I gave earlier was obviously all the diatomics, 7 diatomics. Okay, they're nonmetals. And then water is a nonmetal, carbon dioxide, nonmetal. Sugar, sugar is carbon and hydrogen and oxygen, the sucrose and so forth, all are covalent compounds. Okay, so when we talk about ionic compounds, the question is, why is it that we see in this example, we have calcium and it's followed by 2 bromides? Well, to answer that question, what we got to do is, first of all, break them down into their respective elements first. Break them down into their respective ions and their respective charges. We know that calcium, if you don't know, you should by now, hopefully, calcium on the periodic table is in group 2A, okay? It is a metal, and therefore will lose 2 electrons. And when it loses 2 electrons, now has a net plus charge. Specifically has a net plus 2 charge. Everybody in group 2A, when it becomes ions, will have a net plus 2 charge, okay? The bromides, well, the bromines in group 7, when they become ionic, okay, they're going to have a -1 charge because they're going to pick up 1 electron. And there's 2 of them. That's a subscript. So when we put the ions together, okay, we have to put them together such that the net charge of the compound is 0. So another way to say that is that the number of cations, the number of cations, I don't know what's going on here. There it is. Number of cations plus the number of anions must equal 0. And that's our formula when it comes to ionic formulas. Okay, number of cations plus the total number of cations, total number of anions must be such that you add enough of each so they equal 0 when you put them together. And here the bromides each have a -1. The calcium has a net +2, so I need 2 of them. So that coefficient 2 becomes the subscript in the formula. So I write that as Ca, Br2. Okay. So keep that in mind when we start writing formulas of ionic compounds. And it could work one or two ways. They can say, give you the name, calcium, bromide, give the formula. Okay. Okay. Well, from the name, you should discern that we're dealing with these 2 ions. And these 2 ions, then we know that we need 2 bromides. We can go to the formula. Okay. And alternatively, given the formula, what is the name? That's that nomenclature thing, which, by the way, I've only had like one person try the nomenclature exam. Please get in there and give it a shot. You have multiple attempts. You know, I understand we haven't done a lot, but at least right now, I think I've given enough information at this point that you can probably discern what the name is. But that's okay if you don't pass it. You have a multiple of attempts, and you have until the end of the semester. I didn't change the grade there yet, but I'm going to give you another week to at least go in there and try it. But eventually what I'm going to do is going to input a 0 for everybody, just to alert you that that needs to be completed at some time. Yes, I know the due date is not until the last day of the semester, but you don't want to wait to the last day of the semester, okay? Because it could affect that 10% and affect your grade, depending where you're at in the scale. So anyway, the same as one added fact that I forgot to mention. What I've done is I grouped the homeworks for that exam to be due the day before the exam. I want to group them that way, so at least you know what that means. It says don't wait until the day before, just because they're due the day before to do that homework. You know, if that works for you, you go for it. You know, you go ahead. I group them that way so I give you plenty of time to finish them up before the exam. But you know, I would suggest doing them right after we finish a particular chapter. Okay. And not wait to the last minute for you. Okay. Now sit on that. All right. So let me clear this up. All right, so this question about being diatomic, again, if it was written by Br2 all by itself, then yes, that's bromine. But the fact that there's a metal written first, right here, tells you that you're dealing with an ionic compound and not bromine. Okay. Now the question here is asking you which compounds are ionic. Okay, now obviously, yes, we haven't talked about what they are, who they are. That's okay. You know, I'll tell you what they are after we're done. But you know, you go back and say, okay, what's the definition of ionic? Well, that is a metal, non-metal combination. Okay, very straightforward. So then you just go in here in the list and look for all those compounds that have the metal, non-metal combination. So we take a look at this one, KBr. Obviously, potassium is a metal, and the Br, in this case, bromide, is a non-metal. So definitely that is ionic. Okay. Second one, we got sulfur and oxygen. Both of them non-metal, so that's not, these are not ionic. HCl, hydrogen and chloride, both of them non-metal, so obviously not ionic. And then we got the diatomic bromine, which again, not ionic, because they're both, bromine's non-metal. Carbon and oxygen for carbon dioxide. Again, both of them are non-metal. And then finally, we got the magnesium chloride. Okay, so definitely, only two on this list are ionic. Okay. So very quickly on the names, I'm going to try as I go along and I present these compounds. I'm going to give you the name. That's potassium. First one's potassium. Okay, and then it is bromide. Again, because it's an ionic compound. And then down here we got magnesium chloride. Okay, notice something here. Even though there's a 2 here, we do not call, say, dichloride. Okay, no dichloride. Unlike CO2, where we call it carbon dioxide. Okay. And then obviously the Br2, which is bromine. And then the HCl can be tricky, but when it's not in an aqueous solution where we have AQ, this is just called hydrogen chloride. And you'll see that in a nomenclature that you'll see it listed at H in the nomenclature exam, HCl, AQ. Okay. Most of the time, they may even throw G for gas. If it's just the gas, it's not an aqueous solution, it's called hydrogen chloride. The moment we put water into it, this becomes hydrochloric acid. When it is in an aqueous system, and that is what's roaming around in your stomach, the hydrochloric acid. Hydrogen chloride is not roaming around in your acid. You may have some, but it's dissolved in water, and you have very, very little. It's mostly hydrochloric acid. And then we have sulfur, SUL, FUR, or SUL, PHUR, sounds fine. Either one will work. Tri, because there's 3 oxygens, trioxide. Hope you can read that, trioxide. Okay, sulfur trioxide. Now notice something, I talked about the prefix earlier, the chloride. We have a prefix tri for this. We have a prefix di for this. Only covalent compounds, FYI, only covalent compounds use this prefixes. Ionic compounds do not use prefixes. If you have 2 chlorides, it's simply chloride. Okay, it would be incorrect to name this dichloride. It's just simply magnesium chloride. All right. So of these lists, we identified that there are only 2 that are ionic compounds. Now, when it comes to ionic compounds, and this picture here really demonstrates what's going on with respect to the valence electrons. Okay, remember that here's the nucleus, and then on the outermost shell, we have 1 electron for sodium atom. It's in group 1. There's 1 valence electron. Well, it's a metal, it's going to lose that electron. In fact, it's going to lose it and give it to the chloride atom, because the chloride atom has 7 valence electrons on the outermost shell. And so by sodium losing 1, now it becomes isoelectronic with neon, and it has the octet now as that metal. But what happens is this diameter shrinks. It makes sense, right? Because the outermost layer, sodium has, change the color. Sodium has 3 energy levels. You got this one, and then this one, and then the outermost one. Okay, and the outermost one, we got 1 electron. Kind of not to scale here. Okay, 3 circles here. All right, and so when that 1 electron is lost, well, it's an empty orbital. So it makes sense now that the next one next one in is in the second energy level, and it has 8 electrons around it. Okay, stable state. Driving force is get to the octet by losing or gaining electrons. On the other end of the spectrum, you have the chlorine atom with 7 electrons. It picks up that 1 electron because it has room for it. So now it has 8 electrons in its outermost shell and has a negative charge. But because it picked up an electron, now he's got 8 electrons versus 7. Those electrons now repel. They got a negative charge and they repel each other in that orbital. And so it gets bigger. So the ion for the nonmetal is larger in diameter, and the ion for the metal is smaller in diameter, because one is gaining an electron and the other one is losing the electron. Okay. All right. So that really demonstrates the diameters of the atom and the ions of the respective metal nonmetal situation. And then if we look at the way they're attracted to each other, because they got, like I stated, a positive charge and a negative charge. There's no, in the middle here, just like two magnets come together and attracting each other. That's it. There's no overlap. There's no sharing of electrons whatsoever. Okay. And then you got the crystal lattice here to kind of demonstrate. You have the sodium ions there and so forth. You can see pretty good structure over here on the right side. Okay. Key point here is electrons are completely transferred. With covalent bonds, we're going to learn that there's not a complete transfer. There's a little bit of a partial transfer. Yes, covalent compounds have a little bit of a charge, but it's like a partial weakly charge. And we get more on that when we get to that point. Okay. Now let's consider magnesium and the sulfur atoms. Now consider them as ions. All right. So how many protons and electrons to demonstrate what's going on? So if we take a look at magnesium, magnesium has the atom versus the ion. Both of them obviously have 12 protons, right? If they were to lose a proton, they no longer become, or gain a proton, they're no longer magnesium. The atom, obviously, element number 12 has 12 electrons, 12 protons. The ion, however, now has 10 electrons. So they got 10 negatives, 12 positives. It lost 2, so it has a net charge of a +2, the ion. Okay. If you look at sulfur here, sulfur versus the ion, sulfur atom versus the ion, both of them obviously have 16 protons. Where they differ is the number of electrons. The atom has 16 electrons, but now being a nonmetal and room for 2 electrons, it picks up 2 electrons for a total of 18. Okay, so now its net is a -2. It picked up the 2 electrons that magnesium lost. Okay, and now when we have the ions, we can put them together and they're going to be attracted to each other to write the formula. It would be magnesium sulfide would be the formula. Why? Because magnesium has a +2, the sulfide has a -2. So there's enough cation, enough anion charge to just put them together as a 1-to-1 ratio. So now it is, name-wise, is magnesium sulfide, okay, the IDE, and that's sulfur, which is the atom, okay, that's sulfur. Okay, the nonmetal changes its name, the metal, its name remains. We only distinguish the metal between the atom and the ion. It's the only way we can distinguish which one we're talking about. The anion, we know when we say "ide," we're talking about the anion. All right, so recap ionic size. Cations lose electrons, so there are more protons, obviously. Okay, when the cations have lost the electrons, the outermost shell now is empty. Now there's more protons than there are electrons, and so that nuclear force is really going to pull it in, and so the diameter gets much smaller. Plus, the outermost valence shell that it had before is no longer the case; it's empty. Okay, the anions, on the other hand, you're gaining more electrons, and so they're going to push and repel against each other anymore, and making that orbital that all these electrons are in now bigger. Okay, that was demonstrated in the sodium chloride slide earlier. Okay, so with that being said, we have a series of true and false questions. Okay, so in this one, he says the aluminum atom loses electrons and the iodine atom gains electrons. What do you guys think? You think that's a true statement? What do you think? Does aluminum lose electrons and does the iodine gain electrons? And that would be yes, that's correct, Debbie, because aluminum is a metal and it loses electrons, and iodine is a non-metal when it gains electrons. So that is a true statement. Okay, next one. The aluminum atom, okay, that's where you kind of have to read carefully. The aluminum atom is larger in radius than the aluminum ion. What do you think? So we got the atom versus the ion. What do you think? The atom is larger than the ion. Would that be a true statement? Yes, Jonah, you got it. That will be true. Again, like we explained, the aluminum is going to lose those 3 electrons because it's in group 3. And so that outermost shell can be empty. Now there's more protons than there are electrons, and that pull gets even stronger. So definitely the radius would be smaller. And here it says the iodine atom is smaller in radius than the iodine ion. And that would be a true statement. Okay, because in this case, the iodine gained the electrons, so now its outermost shell is got more electrons, so they're going to repel each other. And then finally, the aluminum and iodine ions form a bond by attraction. Would that be true? Yeah. Will the ions form a bond by attraction? Yes, that would be true. Okay. Now the question is, let's figure out the formula for aluminum iodide, because that's what we're working with here. Okay, because we got the aluminum ion, which we know is A+3, right? Would everybody agree with me that the aluminum ion is A+3? I hope so, because it's in group 3, right? It's a metal, it's going to lose those 3 valence electrons. What about the iodine? What kind of charge does the iodide ion have? Okay. Look on your periodic table. Where is iodide? What group is it in? And then with that information, that should tell you how many electrons it needs to get that magical 8. And it's going to be a -1. That is correct, Jonah. So the iodide has a -1. Okay, the iodide, not the iodine. The iodine is the atom. Here we're talking about iodide. Okay, Now, so we have the aluminum ion plus the iodide. We want to put them together to write a formula. So before we do that, we have to put them together in ionic form first. Why is that? Because we want to know how many of each we need, so they add with enough negatives and enough positives to cancel each other out. So we need here 3 negatives to cancel the positive 3 of aluminum. Therefore, this coefficient 3 in front of iodide becomes the subscript. So that ratio is 1 aluminum to 3 iodides. So that is the formula for aluminum iodide. And you could do the same for aluminum chloride, aluminum bromide, aluminum iodide, aluminum sulfide. They all will share the same formula, okay? And now you can start building up on your database of all the different compounds you have access to. Okay, that's a true statement. Electrostatic attraction. I'm not going to talk a lot about metallic bonding. You're just basically just going to say that metals on the surface are just loaded with a sea of electrons, which makes them very good conductors of electricity, and therefore being good conductors of heat. That's about as much as we're going to talk about with them. So we're going to jump into covalent bonds, where we have ionic bonds where they just attract each other. Okay, now we're actually talking about sharing, actual bond. Okay, now there are 3 types of bonds that you have in covalent bonding. It's a single bond, a double bond, and a triple bond. Now, the way we generally denote that is you can use either a line or the dots, whichever. I suggest just doing the lines. The single bond is denoted by a single line, or you can do 2 dots. Okay, which way you put them makes no difference, just 2 dots. Generally, I want to be consistent with convention. There's 2 dots as follows. Okay, a double bond, we denote that by 2 lines, which represents, each line represents 2 electrons, so we have a total of 4 electrons in that double bond. And then we have a triple bond, which we can denote with 3 lines, okay, which represents a total of 6 electrons that are being shared between two nonmetals, okay, because we are talking about covalent bonds here. Okay, so that is the most bonds you can have with covalent bonds: single, double, or triple. You won't ever see a quadruple bond. Okay, single, double, and triple. Examples of some covalent bonds are carbon dioxide, which we're going to learn about how to write its formula, and we're going to find some double bonds in there. And this carbon is, here we got some space fill models to represent carbon dioxide. We have carbon in the center, and then we have oxygens on the side there, okay? Then we have H2O, good old-fashioned water, or dihydrogen monoxide. That's the technical term for it. It's really interesting if you Google that and look up the dangers and hazards of dihydrogen monoxide, you're going to find some interesting results. It sounds like a terrible gas, terrible chemical, dihydrogen monoxide. It can be if you don't know how to swim. Okay. Anyway, here's the oxygen, and there's the hydrogens there with space fill model. Okay. Some examples of covalent bonds and the 3 types of bonds that we have. Okay, so I just talked about single bond, double bond, triple bonds. We find that with respect to the length of the double bond, meaning a bond between a carbon, a good example is a carbon-carbon bond, which is normally a single bond. A lot of hydrocarbons have that. As compared to a carbon-carbon triple bond, okay? And we're stating here that that bond length between the two atoms for the single bond is a little bit longer and generally weaker than a triple bond, which tends to be shorter between the two atoms, because there's a lot of overlap. There's 6 electrons that are being overlapped and shared, and they tend to be the strongest. Also, the triple bonds have the higher energy involved with it. For example, I'm sure we're all familiar with the cigarette lighters, the butane lighters. That's generally dealt with single bonds. Okay, so a good example would be like butane. Yeah, you got a lot of energy there, but not enough energy like acetylene. Acetylene as acetylene gas in presence of oxygen has enough juice in it, enough energy to actually cut through metal. Okay, and no 2 carbons. Okay, 2 carbons here, but they're all single bonds, and up here less energy than the triple bond. All right, now when we look at the radius of, let's say, the hydrogen atom, this represented here, and the chloride, we're going to talk about hydrogen chloride, okay? The radius of these atoms can be determined, and the radius of hydrogen has 0.037 nm, which is nanometers. That's 10 to the -9. We're down to the atomic scale, okay? I'm sure you've heard of nanobots. Nanobots, the prefix nano means they're down to the atomic scale. And then the radius of the chlorine atom is roughly 0.099 nanometers. It was thought that when they came together to form a bond between them to form the molecule hydrogen chloride, that the sum of each radii would be the bond length of the hydrogen chloride. And so it was believed that the final bond length would be in the order of 0.136 nanometers, which is the sum of the individual radii of the particular atoms. It turns out that once things are measured, that's not the case. That the bond length between the hydrogen nucleus and the chloride nucleus is roughly 0.127 nanometers. Much shorter than what was anticipated, okay? And what is happening is the reason it's much shorter because there is some overlap between the electron cloud of the hydrogen and the valence shell, the valence area of the hydrogen and the chloride to actually form an overlap, okay? Which I'm denoting there. And so where we anticipate them to come together like my fingertips here, it actually overlapped a little bit to actually form a bond. And that's where the difference between the covalent bond versus the ionic bond. Whereas the ionic bond would be more like so, okay? Just attraction to each other. The covalent bond, there's overlap and there's sharing going on with that particular bond, that particular pair of electrons in that bond right there. So that bond will be denoted here by that line right there, okay? And there's overlap. All right, so that is what was found with respect to covalent compounds. We're going to shift gears a little bit, and we're going to talk about bond energy involved here, okay? Bond energy is required whether we're going to break or form a bond. When we're talking about chemistry, chemical reactions, we're talking about making and breaking bonds. And yes, we're going to break a bond, and then we're going to take that broken bond and use it someplace else to make a new bond. And throughout that process, we have energy involved. So the thing is that, for example, when we are breaking a bond, when we want to break a bond, it requires energy. Okay, that makes sense if you think about it. If I want to break up a tree, I'm going to use my energy to break that tree up with an axe, right? Okay, so, and being that it requires energy, energy is treated as a reactant in the process. Furthermore, because energy is required as a reactant, that energy has to come from the environment, and it brings it in from the environment, resulting in that reaction site area to get cold. We call that an endothermic process. And I'm sure you're probably familiar with this. If you go to the pharmacy, for example, and you buy a cold pack, you're out there because you injured your arm, your muscles or something, you need a cold pack. So you go to the pharmacy, you buy this pack and you smack the pack, chemicals are released and that it's cold. That's an endothermic process. Something's going on in there where bonds are being broken, and it's taking energy from the environment, bringing it in, and it actually results in that container getting cold. Okay? And so from a process that we write with an arrow, this is either a chemical or physical process. To the left are the reactants, to the right are the products. So in this case, heat/energy is a reactant. Okay, so it goes to the left side of the arrow. Okay, and what's happening here, we're taking hydrogen chloride, we're breaking that bond, okay, to create the each individual atom, hydrogen atom and the chloride atom. Now, the converse of that is that when we form bonds, energy is released, okay? And we call that an exothermic. So exit's like saying energy is exiting the building, and therefore it gets hot. So again, you go to the pharmacy again, get a hot pack. Okay, you buy a chemical hot pack, and again, you smack the stuff. There's a process going on there that gives off heat, and that package gets warm. Okay, because it is an exothermic process. And in this scenario, energy is a product, so we treat it as a product. You know, it's on the right side of the reaction or the process of the arrow. It is treated as a reactant. Okay. In this scenario, we have a combination. We're taking the same opposite reaction. We're combining the atom of hydrogen and chloride atom to form HCl hydrocarbon. Now you might think about this for a second. We have the hydrogen that if we draw that one valence electron that hydrogen has, we can put a dot there. If we take chloride, chloride has 7 valence electrons, right? Notice something here. Those 2 electrons can come together to form a bond to result in the following. Okay, that is, in this case, can either draw a line between hydrogen and chloride. So in that process, it is an exothermic process. That is bond forming is exothermic, and energy is given off and it gets warm. Okay, so with that being said, here are some questions. Question number 1. Electrons are shared in H2S. Now, again, you may not know what H2S is. That's okay. But I'm hoping by now that you can look at that formula and discern some facts about it. You got hydrogen and sulfur, okay, are together in this formula. What does that tell you with respect to what type of bond is that? Is it a covalent bond or is it an ionic bond? What do you think? Between the hydrogens and the sulfur. What do you guys think? What type of bond is occurring here between the hydrogen and the sulfur? Okay, you only have 2 choices here, right? You have either ionic bond or covalent bond. Now, which one is it? Who wants to give a shot at that? I have a hydrogen and a sulfur. Do I have an ionic bond or do I have a covalent bond? Simply based on what type of element are we working with here? Okay, I got three answers. Yes, covalent. No, not ionic. Two covalents, one ionic. Okay, because hydrogen, now remember, on the periodic table, yes, hydrogen's in the far left, and it's to the left of the stir step. But remember, hydrogen is not a metal. Okay, it is a non-metal, even though it's in the left of the stir step. And think about hydrogen gas, for example. That is not a metal, it's a gas. Okay, it's a gas for one. That should give you a hint. Oh, you mixed up. No problem. It's all right. Okay, so now we have two nonmetals. It means we got a covalent bond, which means, yes, this is a true statement because covalent bonds share electrons. Okay, they share electrons. Second question. We just answered it. The bond between hydrogen and sulfur is ionic. No, it's a false statement because both of them are nonmetals. And therefore, they are covalent bonds. Okay. And then the HS bond is less than the sum of the two atomic radii. What do you guys think? The bond between the hydrogen and the sulfur is less than the sum of the atomic radii. Now, wouldn't that, keep it in mind that covalent bonds are shared and there's overlap. So yes, if you look at the hydrogen radii and the sulfur radii, and compare that sum to the actual bond length of a covalent bond, the bond itself is much less, and that's a true statement. Okay, go back to the couple of slides back to refresh your memory on that. And then breaking the AS hydrogen sulfur bond releases energy, and that would be a false statement because you want to break it. I think of it as chopping the tree down. I gotta have a lot of energy to break that tree down. I gotta chop that bond down. I need energy into the system to break it up. Okay, so this brings us to what are called Lewis dot structures. Okay. Now there's two types of Lewis dot structure. And there's a type that we're going to work with atoms, which is a straightforward thing. You look for the atom, determine how many valence electrons, then you put dots around the atom to represent how many valence electrons they have. Okay, straightforward. Then we're going to deal with Lewis dot structures for compounds, and that's going to whole little process that. Now, from that information for the structures, we're actually going to figure out what the geometry is. Okay. All right, so for the Lewis dot structure for the atoms, this is only true, and this is important. This is only true for the A atoms, groups 1 through 8A, okay? Because we know for sure the number of valence electrons for those atoms. The B's, they vary. It's difficult to determine what they are. There's a lot of factors involved. So this is only for the A. So the group numbers, to refresh your memory, tells us how many valence electrons they are, okay? And so we simply write the formula, and then we put valence electrons. Now, there is a manner, a format that the electrons should be put in. And the best way to do it is think of it, here we got SY for the symbol, and then think of it as an imaginary box around that symbol, okay? All right, 4 quadrants, if you will. So as I fill these electrons by adding dots, I go around the 4 sides, one at a time. Which direction I go makes no difference. Just left, right, counterclockwise, clockwise makes no difference. So I start off with the first hydrogen. okay? Hydrogen has one valence electron. Where I put it, which side, no difference again. You can put it any side. I'm gonna start right there, hydrogen. I could have started down at the bottom or left or right, makes no difference. Helium has 2 electrons, so I go to the next side, okay? And I continue across to lithium. Lithium has 3 valence electrons. That would represent the Lewis dot structure for lithium. And then I keep going for beryllium. Beryllium has, excuse me, I jumped ahead of myself. Yeah, okay, we'll go with that. I'll go around the horn here, but let's do this. I started crossing group 1A with 1 dot, then 2A, 2 dots, 3A will be 3 dots, 4A, the groups will be 4 dots because 4 valence electrons. So starting with carbon, that would be the valence, the Lewis dot structure for carbon. And then I go to well, it's 4A, 5A. See, I go now. I can start filling the sides up with 2 electrons. Each side will eventually have 2 electrons, and I keep going all the way around the horn until I end up in group 8A, which are the noble gases. And so now I went all the way around. Okay, clockwise. I could have gone counterclockwise. Makes no difference. The point being that if you had 2 electrons in group 2. This format will be incorrect, okay? You have to split them up, fill the sides up before you can double up, so that'll be incorrect. Straightforward, nothing fancy. Find what group it's in, put a dot on that side, and you're good to go. All right, so you may ask you, okay, do the Lewis dot structures for potassium. All right, so we find potassium on the periodic table. It is in group 1A. I can put it here. I just go and put it there. That's right. Oxygen is in group 6. So I'll just go around the horn. 1, 2, 3, 4, 5, and 6. Okay, that would be correct. Silicon. Silicon's in group 4. 1, 2, 3, and 4. We're doing carbon. Guess what? Chlorine, but carbon would be the same way. 1, 2, 3, 4, same group, right? Magnesium's in group 2, so I go 1 and 2. And then iodine will be in group 7, so I go 1, 2, 3, 4, 5, 6, and 7. And that would be true not only for iodine, but chloride, chlorine, bromine, and chlorine, okay? Because they're all in the same group. Okay, so that being said, well, there you go. Those are the Lewis dot structures for those particular atoms. Okay, and for any of the other atoms, if they share the same group, they can have the same Lewis dot structure. All right, so which brings us to the Lewis dot structures. Now, what we do here is we look at the formula, and way back when we did an exercise where it showed you some formula and said, well, how many atoms of each we have? How many atoms total? How many atoms of each? That exercise was helping you to identify how many atoms you have in a particular compound. Okay, so with that information, we're going to use that same technique to determine how many atoms we have in the compound we're given, to determine how many valence electrons we have. What that means is this: if your formula has 3 hydrogens, then each hydrogen brings 1 valence electron, so you have a total of 3. Okay. Nitrogen, carbon brings 4. If you have 2 carbons, that means you got to account for a total of 8. That's it. Okay, that's all we do. We tally all that up to tally up the total number of valence electrons we have to work with. And these valence electrons is the total number of valence electrons that every atom brought to the structure of the compound. That number is what we got to work with. We can't magically just take out 2 or 1 or 2 or 1. The valence electrons identify how many electrons we work with, which, by the way, when you tally them up, they should always be a number divisible by 2. okay, to give you pairs. So you end up with total number of valence electrons, divide that by 2, it gives you how many pairs. I like to work with pairs instead of having to deal with individual. Why? Because you can have structures that have 32 valence electrons. I mean, that's a lot of electrons to keep track of. But pairs are very quick. I draw a line, I got a pair. It's very quick, easy way to keep an eye on my electrons. So add up the total number of valence electrons. You're going to know who the central atom is. It'll be given to you. It's either going to be written in bold, it'll be underlined. That's the central atom, which means whatever follows is bonded to the central atom. So once you tally up the total number of valence electrons slash pairs, you draw the central atom, and then you draw a line for everything that's bonded to the central atom, and that quickly accounts for whatever number of pairs you need to get those atoms attached. And I'll do some examples and we'll go through it so you can see the whole thing process, okay? Now, keeping in mind that the octet rule and the duet rule, well, you're only going to deal with hydrogen. And the thing to remember about hydrogen, you will never see hydrogen with more than 2 bonds. Always will be just 1 bond to hydrogen, okay? Because that's its duet. That means that all of the other atoms, you have to arrange those valence electrons such that the octet is fulfilled by every atom involved in the structure, okay? Now, if single bonds don't work, and I'm going to shoot down to the bottom here. If after you've tallied up your valence electrons from number 1, and you put your structures out, and you're like, whoa, I'm shorthanded here, because maybe the central atom is short 2 electrons. What you do is you look to the neighbor who may have the octet, and then they may have a pair of electrons that are not bonded. They're just sitting there. They're unshared. They're not bonded. We call those lone pairs. We can take those lone pairs in the neighbor and create a double bond and see if the octet then is fulfilled for everybody. And if still not, then you go one more. You keep going to maybe even do a triple bond. In other words, taking shared lone paired unshared electrons from the neighbor and creating double or triple bonds until such state that everybody has the octet or the duet for hydrogen. If you can't make that work, that means 1 or 2 things. Go back and check step number 1. It could be that you wrote the wrong number of valence electrons, and that happens. You may be looking at carbon group 4 and inadvertently thought it was 3, wrote down 3, or vice versa. You may have too many electrons at the end and you got no place to put them. Well, most of the time what happens is step number 1 is where the problem went, and maybe you added too many electrons in the beginning, okay? So all along the way, I advocate doing an inventory of number 1 to keep track to make sure that I still have whatever number I calculated of valence electrons all along, okay? Because you can easily lose a pair along the way. All right, I tell you what, let's, I have 2:47. Let's take a quick break, okay? And then I will continue with this particular chapter. And I got 2:47. Let's come back at 3 o'clock, a little bit over 3:01, something like that. Okay, let's do that. All right, right back. Excuse me. Okay, I'm back. And so with respect to Lewis structure, I went over the steps, and then finally here, identify bonding pair and identify what we call lone pair. So if we look at the central atom, okay, for example, we can come up with a formula that is something like this, and I'll give some more examples of this, but let's say we come up with this. Okay, well, carbon's a central atom, and we use the A, B, E general formula. A is always going to be 1. That's the central atom. So we always have A. B represents the number of atoms bonded to the central atom. So in this scenario, there are 4 hydrogens bonded to the central atom. So B becomes B4, okay? That is our general formula. We take that information and we get the shapes table right here, and we look for AB4, and here it is, AB4. Okay, this AB4 came from the Lewis dot structures that we're going to create. That then tells us that here's the generic formula, and so in that example, here's carbon in the middle, and the 4 hydrogens wrapped around it. And it has a very specific name. It's called tetrahedral, and it has a very specific bond angle. That is a bond angle between the hydrogens relative to each other. That is the position, that bond angle is related to the electrons on these bonds here. Okay, that line represents 2 electrons. There's 4 bonds around it. Those electrons are all repelling against each other. So in that configuration, that is the maximum distance that they can get because they're repelling from each other, and they end up with this tetrahedral configuration, which is probably the most common configuration there is, tetrahedral with that bond angle. Now, what can happen is you end up with a different scenario. And we're going to do this one, but let's say we ended up with this formula for NH3. We ended up with a lone pair, and I said the general formula was ABX and then E. Well, let me explain E a little bit further. E represents the number of lone pair of electrons on the central atom. So in this scenario here with nitrogen is A, okay? B in this case is 3 because there's 3 hydrogens bonded around the central atom. Now B they can be the same atom or different. It makes no difference. All we're concerned about is how many atoms are bonded to the central atom, be it the same atom or be it different atoms. In this case, you've got 3. Now, on the central atom, which was what we call the lone pair, there's a lone pair on the central atom, so our general formula becomes E, because there's 1 lone pair. Sometimes you got 2 lone pair, and then Y becomes subscript 2. Sometimes that's it, 2 lone pair. You're going to have either 1 or 2, okay, for the central atom. So now for this particular example, the bonded pair are these right here that are bonded to the B elements, okay, whatever they may be. And then the lone pair are what are on the central atom that are not bonded to anything. So in this example, we end up with AB3. We go back to the shapes table and we look for AB3, and here it is right here. AB3 is a general formula. Here's the configuration, the geometry. Here's that lone pair, okay? And here, that could be nitrogen in the center. We've got 3 hydrogens bonded around it. And it has its own particular name, trigonopyramid. And that bond angle, which we would think would be at 109.5, is much less. And the reason it's much less is this. That lone pair in the central atom, they're not bonded. They're just sitting there in the orbit, okay? They're negatively charged. They repel each other. And therefore, the thought is that they take up more space than just a bonded pair, like in this case here. And so the result is they spread out, resulting in this bond angle to be much less than 109.5, because those lone pair on the central atom take up more space, a lot more space. Okay, so let's run through some examples. and how we can determine the Lewis dot structure and of particular different compounds. All right, so let's take, for example, H2O. Well, H2O, I'll break it down. Here's the sum. We have one hydrogen, okay? Excuse me, what am I saying? Two hydrogens. Now, every hydrogen brings one valence electron. So what I have here in this column is Be, number of valence electrons, okay? From each atom, all the atoms. So we got two hydrogens, it brings in two, hence this number here. And then oxygen, we got one oxygen, and oxygen being in group 6 will bring in 6 valence electrons. So now we have a total of 8 valence electrons, okay? And now I divide by 2 because now what I'm dealing with is pairs. I like to work with pair electrons. The point is that this number 8 is the number you got to work with, along with the 4 pair. That is what you're working with. You have to make the 8 or the 4 pair work. You can't just magically add more if you need more or subtract from that 8, okay? So oxygen is the central atom. So very quickly, we write down oxygen, and then we can see from the formula that the two hydrogens are bonded to the central atom. So we can very quickly draw a line and connect the hydrogen. So that takes care of 2 pair, okay? So now we have 2 pair left from the original 4 pair, okay? Now we cannot put them on the hydrogen because the hydrogen's duet is fulfilled. See, there's duet. But if you count the number of valence electrons on the oxygen right now, at this point, it only has 4 electrons for oxygen. There's 2 electrons around hydrogen on each hydrogen, but only 4 around the oxygen. So it is shy 4 electrons or 2 pairs, and here they are right here. So all we got to do is simply put them on the oxygens. And you can put them as a line like I just did, or you can put them as dots. Makes no difference, whichever you're comfortable with, one or the other. So that took care of my 2 pair. I got 0 pair left. I go back and check, make sure I still got 4, 1, 2, 3, 4 pair, or a total of 8 valence electrons. So I'm doing an inventory. I'm still got the 8, okay? So that is the formula, the structure that I come up with. I got oxygen 2 bonded to the hydrogens and 2 lone pair on the central atom. Now I've determined the general formula. So obviously I got A is always there. That's the central atom. B represents how many atoms are bonded to the central atom, and there are 2 hydrogens bonded to the central atom, so we got a subscript 2. And the lone pair we identified are on the central atom. In fact, there are 2 lone pair. So that becomes, the general formula becomes AB subscript 2, E subscript 2. That is the generic formula for H2O, which means that we go now to the shapes table and we look for AB2E2, which is right here. Okay, so you can see here's the geometry. This center represents the oxygen, and then the 2 hydrogens right there, with the 2 lone pair on the central atom, which, as I explained earlier, they take up a lot of space. You know, with the previous example we did, they take a lot of space, but now I got 2 pair, they take up even more space. The resulting is that bond angle, which started off at 109.5, now is much, much less than 109.5. It really got pushed in, okay, because of the 4 lone pair of electrons on the oxygen. And it has its own specific name called bent, that geometry. Totally different from trigonal pyramid, which only has 1 lone pair, okay? All right, so back here. basically a rehash of what I just talked about, okay? 2 lone pairs, and we end up with that structure, that formula. And then from there, we go to determine the general formula of AB2E2 for the shapes table. That tells us the geometry and the specific bond angle associated with that formula. Okay. All right, well, let's try a few more, okay? Granted, we don't know what they are. You may or may not know what these formulas, what these compounds are, and that's okay. We're not concerned about that. I want you to identify how many of each elements are in there in that particular formula. And from that, we determine how many valence electrons. So let's take the first one, HCN. Okay, well, we see we got 1 hydrogen, okay, which brings us 1 valence electron. We got 1 carbon, okay. This is my systematic approach of the problems, and you can follow my format, and then eventually build your own. But I do it this way, like you crack. I got to go through this of all the atoms. I got no questions about how many valence electrons come into play. 1 carbon, it is in group 4, okay, and 1 nitrogen, okay. The nitrogen is in group 5, so I got 5 valence electrons. I have a total of 10 valence electrons or 5 pair to work. So that's my numbers, 10 and 5, that I need to work with. And I can't deviate from that. That is what I have based on the number of atoms that are in the formula. So carbon here is identified as the central atom. So carbon, I can quickly write carbon. And then since I got hydrogen and nitrogen, I can just very quickly just attach the nitrogen and the hydrogen. Well, that takes care of 2 pair, okay? So I got 3 pair left over, and I need to put them someplace. Obviously, I cannot put them on the hydrogen because, again, hydrogen only has 1 bond. Will always have 1 bond. You won't find hydrogen with more than 1 bond, okay? Now, at this point, I can put those 3 pair anywhere I want on the carbon and nitrogen, totally up to you. Makes no difference because eventually we're gonna get to the same spot. I just prefer to put them on the outside atoms, and then if I have any left over, then go work my way to the center atom. So I start with the outside atoms, get those filled up, and then come into the center. I got 3 pairs, so I can very quickly just put them on the nitrogen, okay? And that takes care of my pair. I go back and do an inventory to make sure I didn't lose anything, and I still have 5 pairs. 1, 2, 3, 4, 5 pairs. So I'm good to go. Okay. Now I go check my duet octet. Obviously, hydrogen's good to go. Okay. Hydrogen is good to go. It's got its duet. The nitrogen on the right side has 8 electrons. You got 3 of them that are lone pairs are on the nitrogen, and one pair that's shared with the carbon. So it has 8 electrons. It's good to go. Carbon has a total of 4 electrons. 2 of them are shared with hydrogen. 2 of them are shared with the nitrogen. It's not fulfilled the octet. So here's where we borrow from Peter and share with Paul, okay? Borrow from the neighbor who's got lone pair, create a double bond, and then check the octet and see that everybody's happy. And if not, do it again until everybody's happy with the magical 8, okay? And so keep in mind, I still have 5 pair here altogether. So I'm gonna quickly just gonna take this pair and just create a double bond. So now I have this scenario. I'm gonna keep those pairs where they were so we keep track, okay? So nitrogen still has 8, so it's good to go. 2 of them, or 2 pair, are shared with the carbon now because of the double bond. And then 2 pair are lone pair on the nitrogen, so it's got 8. Hydrogen obviously is okay. Carbon now went from 4, now has 6 electrons around. 2 pair are shared with the nitrogen and 1 pair shared with the hydrogen. So it's not quite at the 8. So what do? Now we create a triple bond. So what I'm going to do is I'm going to change the color a little bit. So I'm going to take a pair and just create another bond. So now what I have is a triple bond between the carbon and the nitrogen, okay? And then my hydrogen bond, okay? Go do an inventory, make sure I still got 5, 1, 2, 3, 4, 5. So I still got that 5, I haven't done anything. And I check inventory every time because I can easily lose electrons along the way, and I can easily add more along the way inadvertently. Okay, so I'm checking every step. Now check my octet. Well, nothing's happened to nitrogen. Nitrogen has been sharing this lone pair, so nitrogen still has a pair. Hydrogen's good to go. Now carbon now is good, and now it has 8 valence electrons. 1 pair is shared with the hydrogen, and 3 pair are shared with the nitrogen for a total of 8. So now carbon is octet full, and when we draw it over here, we got a triple bond. I'll go ahead and put 2 dots there on the nitrogen, or line, either one. And now that is the formula we come up with, okay? The general formula, carbon is A, and then B2. Notice that B, we stated earlier, as I stated, B can be the same element or different elements attached to the central atom. In this case, we got a hydrogen and a nitrogen, but there's still a total of 2. So the general formula is AB2. With that information, we go to the shapes table and look for AB2. And AB2 would be up here on top. Here's AB2, okay? Here's the geometry. This is carbon, here's nitrogen, here's hydrogen. There's a bond angle of 180 degrees between the nitrogen and hydrogen, and it has its own little name called linear, okay? It's a linear species. Notice up here another linear. Normally, when you have a compound that only has 2 atoms, there really isn't a central atom. You have a central atom when you have at least 2 or more atoms attached to a central atom. But if there's only 2 themselves, it's an automatic linear. That's all the configuration you can have. There's nothing else, other configuration you can have when you only have 2 species there. Okay. All right. So for HCN, it has a linear shape, its geometry, and it has 180 degree bond angle. All right, so now that is what we come up with, what we came up with, okay? All right, and this geometry, what we're doing is important because the next step, we're gonna be talking about polar and non-polar bonds, okay? And then for that information, it's going to tell us whether the molecule is polar or non-polar. Once we know that the molecule overall is polar or non-polar, that tells us more information. See how everything's all tied in, put in together, how we can gather a ton of information based on all these electrons. It's all about the electrons. All right, let's do the next one, which is what we call fluorinated hydrocarbon. Okay, nasty compound used to get up in the atmosphere and destroy our ozone. Anyway, we have 1 carbon, which brings in 4 valence electrons, 1 hydrogen, 1 valence electrons, and we have 3 fluorides. Okay. I put a 4 there and a 1, they're saying how many amounts. So 3 fluorides, excuse me, fluorine is in group 7. Okay, so it's 3 times 7, so it brings in 21 valence electrons. 21 valence electrons. So tally this up, I end up with 26 valence electrons to work with. That is my number. Okay, or 13 pair, because each line represents a pair, that go 13 pair. All right, the carbon is a central atom, so I can very quickly put carbon down, then I have a hydrogen and 3 fluorides bonded to the central atom. So I can quickly draw those. Here's my hydrogen and then 3 bonds for the fluoride. For the 3 fluorides, okay? That takes care of 4 pair. So I have 9 pair left over after I put in the initial compounds. All right. Now, where to put them? Remember, the octet. If it hydrogens, we're good to go, always good to go. Once you put 1 bond on hydrogen, that's done. You don't have to look at them anymore. So the carbon has 4 bonds around it. 4 times 2 equals 8. So the octet is good to go for carbon in the center. Okay. So the only place these 9 pair can go is on the fluorides. Okay. So starting from the outside, working my way in, I'm just gonna put 9 pair. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9. Then this 9, 10, 11, 12, 13. I still have 13 pair. Okay, that's what I started off with. I didn't lose that. All right, check my octet. All the fluorides are good. 1 pair is bonded to the carbon and the other 6 are on the fluoride itself. So I got 8. Okay. The other 6 electrons are the other 3 pair on each fluoride. So each fluoride has the octet, the carbon has the octet, and the hydrogen has a duet. I still have 13 pair total. I'm good to go. That is my structure. Okay. Now I do my general formula. Carbon is A, and then I got 3 moieties bonded around the central atom. So 4, excuse me, we're missing 3. So that is my general formula of AB4, okay, for this CHF3. So that tells me now to go to the shapes table and look for AB4, which happens to be right there. Oh. Okay, right there, AB4. It is the tetrahedral, the most common configuration found in nature, 109.5. So, here we got carbon here. This could be the hydrogen, then the 3 fluorides around it, like so. Okay, tetrahedral. Bond angle 109.5. All right, let's see. There is the structure. All right, now here's one more very interesting one because it's going to give us a lot of information with respect to the compound itself. The next one's carbon dioxide. Keep in mind, we're just working with covalent compounds, okay? All right, let's start off with, I have 1 carbon, brings in 4 valence electrons, 2 oxygens. 2 oxygens are in number 6, so I got 12 valence electrons coming in from the oxygens for a total of 16 or 8 pair. Okay, I got 8 pair of valence electrons. Carbon is the central atom, and there's 2 oxygens bonded to that. So I can quickly write carbon first and then just draw 2 lines and attach the 2 oxygens. Okay, that takes care of 2 pairs. So I got 6 pair to work with. Now, as I stated before, I always put them on the outside elements and work my way in. So I'm going to put 6 around there. I go 1, 2, 3. I can't add any more to this oxygen on the left. Why? Because the 8 has been fulfilled. Okay, so that's 3, 4, 5, and 6. Again, check that took care of my pair. Check to make sure I still got 8 pair total, and I do. I got 8 pair, so I'm good to go. Now check the octet. The oxygen on the left has 8 electrons around it. 3 of them are lone pair and one of them is paired. 8 electrons or 4 pair. One pair is bonded, 3 of them, 3 pair are not bonded. The same is true for the oxygen on the other side. Okay, similar situation, 1 bonded pair, 3 non-bonded pair. The carbon now only has 4 electrons around it, which are being shared with the oxygen. So obviously it is short 4. So as we did for this species here, we're going to borrow from the neighbor. In fact, we're going to borrow from both neighbors. I'm going to take one of these and make a double bond there, and then take one of these and make a double bond there. When I do that, I end up with a double bond right here, oxygen, and then my 2 other lines are still there. Double bond on the left side, 2 lines on the left side, oxygen. Go back and check to make sure I still got a pair. 1, 2, 3, 4, 5, 6, 7, 8. I didn't lose anything. I'm still good to go. That is the formula. I got a carbon double bonded on both sides, left and right, a double bond with oxygens on left and right. And that is the formula for carbon dioxide. The general formula would be AB2, which would be the same as what we did for HCN, which would be a linear species. You can go back to the shapes table and look up AB2, and bond angle here would be 180 degrees. And it's linear configuration. Okay. Now, the fact that we ended up with that type of a structure is very important down the road here when we talk about polarity, because of this structure, it results in a property for carbon dioxide that we wouldn't anticipate that it had, but because the way it is put together structurally, it has a particular property, and we'll dwell on that here in a bit. All right, so here's the formula. All right, let me then we have the last one. Let me clear this up, get some more space in here. Okay, we have ammonia. This is the formula for ammonia. Okay, we got 1 nitrogen, okay, which has 5 valence, excuse me, I put the letter V, 5 valence electrons, and I got 3 hydrogens, which brings in 3 valence electrons. So we have a total of 8 valence electrons, or 4 pair to work with. Okay, the nitrogen is a central atom, so I can quickly write nitrogen. I have 3 hydrogens bonded to it, so I can draw 3 bonds real quick and attach my hydrogens. That takes care of 3 pair, and so I have 1 pair left over to work with. Now, obviously, I cannot put it on the hydrogen, okay, because the duet would be violated. So the only place I can put them, and I'm just going to make double dots, and we'll leave it at that. Okay, it has to go in the nitrogen. Okay, check the octet, duet, good to go for the nitrogens. Around the good to go for the hydrogens. Around the nitrogen, we have 3 pair, bonded pair, and 1 lone pair. Okay, so we get a total of 8. So the octet is fulfilled for the nitrogen. Okay. All right, so the general formula will be A for nitrogen, B3 for the 3 hydrogens, and then we will have an E because there is a lone pair on the central atom. So it's A, B3, E is the general formula, which then we go to the shapes table. I tell you we'll be using the shape table quite a bit. We look for AB3E, and there it is. That's the general formula. It has a specific name, trigonal pyramid. Its bond angle is 109.5. Here's the general geometry. We got the nitrogen sitting there in the middle. We got the 3 hydrogens sitting there, bonded around the nitrogens, and then we get that lone pair. That lone pair, again, is taking up space, resulting in that bond angle to be reduced much more from the our reference point of 109.5. That lone pair takes up more space, so it kind of squeezes the bond angle of the others in. All right, so here's finally right there. And that is the formula for the structure formula for ammonia. Okay. All right. This particular page is the HCN that we did initially, just a breakdown of it. HCN, we added up all the valence electrons. We had 5 pairs to work with. We quickly put carbon as a central atom, attached to hydrogen and nitrogen. We got 3 pairs left. Okay, so I just put them around wherever you want to put them, except the hydrogen. I put them here around the nitrogen. Okay. And then I checked the octet and we continued, we made a triple bond. We made a triple bond to make sure that the octet is fulfilled for all the atoms except for hydrogen. And notice there, we still have a total of 5 pair of electrons, okay? So if you ever, get to this point and you end up with, you're short with electrons, then check to make sure you did your tally correct. Fact that you selected the right number of valence electrons. It could be possible you're thinking it's a group 5, but in reality maybe, and you put a 4 down instead of a 5, okay? Or something that you go the other direction. Maybe you added more electrons, so somehow you end up with more electrons than you can put any place. Again, go check your math and make sure that you selected the correct number of valence electrons. Okay. Keeping in mind that the final tally of valence electrons should always end up to be divisible by 2. That represents a pair of electrons. Okay. So if you end up with number 9, then obviously something happened, right? Any odd number should send up a flag until you go back and check it. All right. So what this brings us to is doing what are called the polyatomic structures, Lewis dot structures on what are called the polyatomic ions. So what are those? Well, I'm glad you asked. Let's go to the good old periodic table. I told you I'll be using this quite a bit. We've only touched on this, but we're going to use this information here, this information, and now we're talking about this information. On the bottom left corner, there is a table of what are called polyatomic ions. Now, this is not by no means an exhaustive list of all the polyatomic ions out there, but it's for the most part the ones that we deal with here. Okay. And the thing about this aspect is that these polyatomic ions are, point number 1 is they are covalent compounds. Okay. But the nature of the beast is such that these started off as covalent neutral species, but during the chemical process, they had a charge on them. Okay. Most of the time, these guys started off as acids and then reacted with the base, which is the type of reaction we're going to talk about. And the result is these polyatomic ions. So, for example, the NO3 has a negative charge. That initially came from nitric acid, by the way, to form this nitrate. But it is an covalently bonded species, but because it's also a salt, okay, has a charge in it. So the nitrate has a -1 charge and the nitrite has a -1 charge. Let me quickly introduce you. Nitrogen. Obviously, we have nitrogen in the element. Its particular name is nitrogen. When nitrogen becomes an ion, it picks up 3 electrons. Now we have nitride. Okay. Then we have nitrate, which is the NO3. It is nitrogen bonded to oxygen. Notice the name, nitrate. When there are three oxygens bonded to the nitrogen and the whole thing is a negative charge, is an ion. We can, and we get the nomenclature, we're going to talk about this quite a bit. If we also have another species that has two oxygens rather than three, and that one is called nitrate. So in essence, you have like three types of nitrogen, right? You have the nitrogen, the element. When nitrogen, the element becomes an ion by itself, just the element nitrogen, it's called nitride. When the nitrogen is bonded with three oxygens and it has a negative charge, it's a unit, and we call that unit nitrate. And there's two oxygens, we call that unit nitrite. And the same thing would be true for the sulfate, because we have sulfur, sulfide, sulfate, sulfite, okay? And that's the main difference there. Takeaway from all this is that we're going to be doing Lewis dot structures for these polyatomic ions. FYI, these ions stick together as a unit. We don't separate them. They have their own specific name, like the one I just marked right here. That is called nitrate. We don't change it to nitrogen oxide or anything of the sort. It's called nitrate. Okay. If we ever need more than one to be represented, we put a parenthesis around it with a subscript. 2, 3, 4, whatever number we need. So we will do the same steps with these polyatomic ions as we did with the covalent compounds to determine the geometry, okay? The only difference is we have to add a correction factor for the chart. We either have to add or subtract from the valence electrons that we collected based on the charge that they have. And I'll give some examples of how we're going to do that. That's the only difference. And then the second difference is when we finally get the structure, we put a bracket around it, around the polyatomic ion, and then with its respective charge in the upper right, okay? So we do the same 4 steps as we did before. Now, we add a correction factor. If that polyatomic ion is a negative in charge, like the nitrates and the nitrites, then we're going to add a correction factor. And that the amount of correction factor depends on the charge. If it's a negative 1, we add a 1. If it's a negative 2, we add a 2, etc. Okay? If it's a positive polyatomic ion, the correction factor is subtract. We subtract. Okay? We're not really removing electrons or adding electrons. We're doing a correction factor. So this really should be corrected. It will become clearer when we show you the reactions that are going. I'll show you an example of what's going on here in a minute, why we add this correction factor. So the takeaway at the immediate part is this. If it's a negative, we add to the valence electron count. If it's a positive, we subtract, okay? Okay, then at the end, we put a full bracket around it, and then we add a negative charge around the whole thing. For example, let's do this one, NH4, which is really the only cation, polyatomic ion that we see. We see others, but we deal with this one quite a bit. So we have 1 nitrogen, okay, and we have 4 hydrogens, right? So the nitrogen brings in 5 valence electrons, and there are 4 valence electrons. Now, notice if we were not to add or subtract here, we would add this up as 9, right? 9 valence electrons, so there's a problem there, right? We get an odd number. That won't work. So the fact that it is positive, we're going to subtract. Our correction factor is to take 1 away. So we have 8 valence electrons, which gives us 4 pair. Nitrogen is the middle component. So we got nitrogen, and then we quickly draw, like we've been doing before, the 4 hydrogens around it, okay? And that takes care of the 4 pair that we had to work with. Then we put a bracket, not a parentheses, but a bracket around the whole species and its respective charge on the upper right corner of the bracket. So that is the format we present the structure, the Lewis dot structure for the polyatomic ions. Everything's the same except two. We either add or subtract a correction factor depending on the charge of the ion. Then we put a bracket and the charge at the upper right corner. At this point, now we can determine the general formula like we did before. Nothing new here. We got A, B, 4. That is our general formula. You go to the shapes table, you'll find it to be tetrahedral, and you find the geometry given there to be tetrahedral, and the bond angle there will be 109.5. Okay, so that's the steps. That's it. Add or subtract a correction factor, write the Lewis dot structure, put a bracket around it, and then the respective charge on the upper right corner. Okay, and that's what we come up with right there. All right. Right, here are some examples. Okay. We have the BrO3, okay, and down at the bottom is another polyatomic ion, sulfate, and then the cyanide. You'll find the SO4 -2 and the CN in our polyatomic ion table. Anyway, what we do, let's take the one in the upper left corner. It's a bromide. Bromine has 7 valence electrons, okay? There are 3 oxygens for a total of 18 valence electrons. It is a negative polyatomic ion, so we need to add a 1, a correction factor. Okay, so we have a total of 26 valence electrons, or a total of 13 pair. So with that information right here, and knowing that the Br is the central atom, I can quickly write Br and then draw the 3 oxygens around it. Okay. And that took care of 3 pair, right? So I got 10 pair to work with. So I'm going to put those around. I'm going to go outside and work my way in. So I can put 3 pair around each oxygen because each one's already bonded. So I can go 1, 2, and 3. And that's taken care of right there, the 8, 4, 5, and 6, 7, 8, and 9. So that's 9 pair. I got 1 pair left over. Well, I can't add them anyplace else other than the central atom, which is the bromine. And so now I go back and check. That takes care of that. I still got 13 pair. I simply put a bracket around it and then a negative charge on the outside. Oh, negative charge on the outside. Okay, and that is my structure, my Lewis dot structure, the bracket and the charge on the outside. My general formula will be A, B, 3E. Okay, A, B, 3E. I got 3 oxygens around it, and then I got a lone pair on the central atom. So then go to shapes table. AB3E, and there it is right here. Okay, trigonal pyramid, angle less than 109.5. And so here we got the bromine in the middle, the 3 oxygens around it, and then the lone pair on the bromine. Okay, here it is. The left bracket, the image got cut off, but that is a bracket on the left-hand side. All right, so the next one would be SO4, similar situation, same situation, not similar, same. I got 6 valence electrons coming from the sulfur. We got 4 coming from the 4 oxygens for a total of 24. I got a -2 overall charge, so my correction factor is a +2. So I got a grand total of 32 valence electrons or 16 pair. The sulfur is the middle. central atom, so I can write that real quick. I got 4 oxygens, so I can bond in the 4 oxygens as so. Okay. And that took care of 4 pair. So I got 12 pair here to work with. Obviously, I cannot add any more to the sulfur because I got 8 around the sulfur. So the only place they got to go will be around each individual oxygen. So I can add 3 more pairs for every oxygen to give me a total of 12. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the inside 13, 14, 15, 16, which is the number I started out, 16. Okay. I put my bracket. Students tend to forget to put the bracket and then my negative charge. And there's my Lewis dot structure for sulfate. This is the sulfate polyatomic ion. The generic formula would be AB4. A is the sulfur, 4 oxygens. If you look that up, I won't do it, but that is tetrahedral. Okay, tetrahedral. All right. So then you come up with this. All right. So now the last one is the cyanide. Recall when we did the very first one, it was HCN. Remember that one? We had the hydrogen here. What's happening here is that hydrogen has been removed and you end up with a negative charge on the carbon. Anyway, same process here. We got 1 carbon, 4 valence electrons. Nitrogen has 5, okay? And because it has a negative charge, okay, we need to add 1. When we did, there's a correction factor, okay? What's happening with all these other ones is normally there's hydrogens on them, like the HCN we just did. Well, in this case, it's been reacted on, it's form a negative charge on the compound we're looking at, the polyatomic ion, but we have to account for that charge. And when we did the HCN, we had 1 hydrogen, so we added 1 for the hydrogen. In this case, we don't have the hydrogen, but the electron's there, so we have to correct for that factor. That's what we mean, I call them correction factors. We're not really adding electrons, they're already there. We just take accounting for them, okay? And so we got 5 pair. And if you go through the process, you'll find out the same structure we did earlier for HCN. If you recall, we had HCN bonded to the carbon, a triple bond, nitrogen, the double bond. Okay, that was HCN. This is the cyanide. Cyanide, you all heard of potassium cyanide. This is a very poisonous salt. Okay, so that, don't forget the brackets, not the parentheses, but the brackets, and then the negative charge in upper right corner. Okay, now you can tell here, as a case for HCN, there's only two species, so there really isn't a central atom, and so it's linear. Geometry is linear. Okay, no bond angle to think of, because to have a bond angle, you got to have at least 2 atoms bonded to a central atom. And that's not the case here. All right. So, which kind of brings us to what's called the VSEPR, which is what I've been kind of introducing to you when I've talked about the lone pair of electrons. And that's because, remember, these bonds are electrons, either bonded or non-bonded. But these electrons are negative charged on this bond, and they're going to repel each other, not even within a cell, but with other bonds. And they're going to repel each other such that they're going to position themselves to maximize their distance from each other because of repulsion. That, in effect, results in affecting the structure of the compound, which then also affects the chemical properties and the physical properties of compounds because of these electrons, okay? And so lone pairs and bonded pairs, they will repel. That's what we talk about. So they give it this acronym that stands for valence shell electron pair repulsion model, okay? So I talked about the general formula ABE. A is the central atom, B is the outer atoms that are bonded to the central atom, okay? And E represents the lone pair of electrons bonded to the central atom. That's important, only to the central atom. We don't really care about the lone pairs on other atoms. That has nothing to do with our general geometry, only to the central atom, okay? When you have two species, so all the diatomic elements, all the 7 diatomic elements would have just a simple linear. Anything with only 2 elements attached, like the cyanide ion, we have a linear geometry, okay? Carbon dioxide, which we just did, the general formula was AB2. And because the double bond between the carbon and oxygen, it forces it to have this linear configuration, okay? So carbon dioxide is an example of an AB2, bond angle 180 degrees, okay? There is another geometry called AB3. You've got A, central atom, and 3 species bonded to it. It's a planar species, very symmetrical because it's 120 degrees all the way around in this example here. 120 degrees, and maybe slightly, but for our purposes, 120 around here. Good example of this is this species here, which is formaldehyde, by the way. This is the formula for formaldehyde. Here's carbon, here's the hydrogens, and then the double bonded carbon oxygen species on top. Very hazardous species, has been shown to cause cancer. All right, our tetrahedral, which I mentioned is our standard, kind of most common geometry that's out there. Bond angle 109.5 has the AB4 general formula. Okay, this is an example of methane, a hydrocarbon, carbon here in black, and then the 4 hydrogens wrapped around. This is kind of show you a 3-dimensional model of this. Now, keep in mind, this bond, every bond, these 4 bonds are electrons, 2 electrons there. And they're going to repel each other such that they're going to maximize their position as far away as they can from each other because of all the negativity charge, if you will, that electrons have. Okay, so with that being the case, that's the maximum configuration they're going to have. Now, yes, they will bend, they will twist a little bit, but they're all going to spring back to that configuration. Okay, we have the AB2 configuration, which is classified as bent. Okay, in this scenario, AB2E, there is a lone pair of electrons sitting there, which is forcing that bond angle to be much less than 120 degrees. Okay, one would anticipate that this would be like the AB3 species, but it's not the case because those electrons right here on the central atom cause it to bend. Now, sometimes, people look at SO2, which is sulfur dioxide, and then compare it with carbon dioxide and say, hey, structurally they're the same. Well, that's not the case. We just did carbon dioxide and we found the geometry to be as follows, if you recall, okay? And it was a linear, it was a AB2 geometry being linear, okay? So even though they share the same number of atoms, they differ in as far as the number of valence electrons being brought. Sulfur brings in more valence electrons, resulting in having to put a lone pair on the central atom, which changes the whole configuration. Okay, where are we at? And then let me go through, finish these up, and then we'll call it a day. Then we got the AB3E trigonal pyramid. We've done this example, which was ammonia. Okay. Again, the bond angle is much less than 109 because up in here we have a lone pair of electrons that are pushing these bond angles into each other, resulting in a bond angle much less than 109.5. And then we had the infamous water configuration, which is also called bent, as the previous one showed. And this species here, we have two lone pairs on the central atom. Okay, two lone pairs, which, you know, if we were to kind of draw it out. Here we got the two lone pairs there, really driving that bond angle to really be much, much less than 109.5. Okay, 109.5. Now, the thing to remember, one thing to remember when we start doing configurations, that whenever you end up with lone pair of electrons on the central atom, that makes that molecule, gives it a certain property 100%. Okay, and that property is what we call polar versus non-polar. The best example I can tell you right now at this point in time is polar. Think of it as, say, water. Non-polar, think of it as oil. Okay, we know that oil and water do not mix. Don't believe me? Check out the Italian dressing. Okay, you got two layers in that bottle. You let them separate. You got two layers, an oil layer and an aqueous layer. They won't mix. Even if you shake it up, they're just going to form an emulsion. And that's because of the properties of the oil, which are non-polar, and the properties of the water, which are polar. Okay, and what happens is that whenever you end up with a Lewis dot structure as a kind of a very good general guideline, whenever you end up with lone pairs in the central atom, you end up with a polar species, which then allows us to predict whether that compound is more soluble in water or more soluble in oil. Okay. Just a couple more here, I believe. Yeah, let's stop it here. So basically, be able to, from this point, you know, what we talked about, given any covalent molecule or polyatomic ion, you should be able to draw the Lewis dot structure. Okay. And then from that information, using the shape table, determine the shape and the particular bond angle for that particular molecule. Okay. Don't forget, if you're drawing the polyatomic ion, that you will put that in brackets with their particular charge in the top right, be it a negative or positive charge. Okay. Try these two molecules at home is pH 3 and ozone. Ozone is, yes, the same ozone that you see down here, or you hear about ozone warnings. That's not very good to have a lot of ozone down in this area, but there's another ozone that's up in our atmosphere is very important. It is important in that it will protect us from the UV light. So what I'm going to do here is we're going to stop it at slide 31. And we will continue with this one next Friday. Okay.